Okay, so I believe we left off with the results of the Michelson-Morley experiment, which were a complete failure. There was no detected motion of the Earth through the ether, which raised the question then, basically, what the hell is going on? Why can't we detect the motion of the Earth through the ether? So a gentleman named Hendrik Lorentz, that's him on the right, and this here, if you haven't figured it out, is Albert Einstein, when he was much younger. So Lorentz pointed out basically that everything works out if you assume that things in motion contract in the direction of their motion. Okay, what does this mean? So the problem with the Michelson-Morley experiment, going back to here, was that this path should have taken longer than this path when the Earth is moving into the ether like this. Okay, when the Earth is moving this way, this path, L2, should take longer than L1, okay? And it didn't. So Lorentz's then correction for this, or idea to correct for this, was simply that things get shorter this way. And he didn't actually come up with it in response to the Michelson-Morley experiment. He came up with it, I believe, because it made electromagnetism work correctly. It made Maxwell's equations work correctly under relativity. But point is, it also worked for the Michelson-Morley experiment. So he said, well, the reason this path isn't longer is because it actually gets physically shorter. How much shorter, you might ask? Well, enough to make the length of time on those two paths equal. Whoops, I went the wrong way on my slideshow. Hang on. Okay. So, and then also to make everything work out and make the speed of light be the same in all reference frames, things in motion have to experience a slower passage of time. So the amount by which they get shorter or slower is this factor called the Lorentz factor. So this symbol here is a Greek lowercase gamma, okay? Third letter of the Greek alphabet. It looks like a little sort of a cursive Y when you do it like that, but it's a Greek gamma, okay? And it's equal to this, okay? Where V is the speed you're going and C is the speed of light. Here's a plot of it with V over C on the horizontal axis and gamma on the vertical axis. And what you can see is this factor is 1.0, or very close to 1.0, for any reasonable speed you might be traveling at in everyday life. Remember that the speed of light is 3 times 10 to the 8th meters per second. So if you're going 10% of the speed of light, right here, you're traveling at, well, dang it, you're traveling at 30 million meters per second, which is way faster than you would ever go in your life. So we live down here. We live down here in the realm where gamma is equal to 1, okay? And so we don't ever notice these effects in our everyday lives, okay? But if you were to go close to the speed of light, you would find these effects taking place, okay? What are these effects? So the Lorentz contraction, this is the slide I just accidentally showed you, okay? The Lorentz contraction basically is this idea that objects get shorter in the direction of their motion. So this is a picture of Hendrik Lorentz. It's a perfect square, okay? And this is when he's not moving, okay? So he lives in a box that's a perfect square when it's not moving, okay? Here's what happens if it's moving to the right at 60% of the speed of light, okay? In the reference frame of an outside observer, it gets shorter, okay? The factor gamma, if you plug in V equals 0.6c into this equation, what you'll get for this factor gamma is 1.25. And then what you'll get is that the length of it in the direction it's moving will only be 80% of the rest length, okay? As he's moving faster, moving at 90% of the speed of light, he's down to less than half of his rest length, okay? And asymptotically, as you approach the speed of light, your length shrinks to 0. Okay. Now, if you have mass, you can't reach the speed of light, so you'll never reach this point where your length is 0, but you'll asymptotically approach it as you approach the speed of light. Why don't we notice this effect? So one reason, obviously, is what I just told you. It only takes effect, it's only significant at high fractions of the speed of light, and we don't travel at high fractions of the speed of light in our everyday lives. The other reason is because if you're trying to measure this, say Lorentz is living in his box, and say his box is 1 meter square, and he has a meter stick, and he can measure the distance between, say, the top and bottom walls and the left and right walls, and he finds they're both 1 meter. That's fine. Okay. Now say he's going at 60% of the speed of light. He uses his meter stick to measure this way, and finds it's still 1 meter. Now, if he tries to turn it this way and find that it's only 60 centimeters wide, what will happen is the meter stick will also get shorter in this direction. So any measuring device you use to try to see the Lorentz contraction when you're the one actually moving will then change size itself and basically foil you. Okay, so this effect here, where you get shorter in the direction of motion, is only visible to an outside observer. Only someone standing out to the side watching Lorentz go by would see this. Okay, so whoops, sorry, boy, I can't go the right way at all in my thing. And then time dilation. This is something you could see too. Basically, if you're moving at a significant fraction of the speed of light, time moves slower for you. Time passes slower. So if if your friend sends you a message saying, hey, get to school, you need to be here in 5 seconds, and you go up to a significant fraction of the speed of light, you'll get there in 5 seconds as your friend sees it, but it will only seem to take 4 seconds or 3 seconds to you. Okay, you'd have to be pretty far away from school. You'd have to be out well past the orbit of the moon to be able to spend 5 seconds traveling at a significant fraction of the speed of light. Anyway, but when in motion, time seems to pass more slowly. We won't spend too much time on that because that's not as quite as trippy as the length contraction. Okay, so here, the top half of this slide is just a summary of what Lorentz said. Okay, and Henri Poincaré, a French mathematician, pointed out basically a year later that if the Lorentz transformation holds, all inertial reference frames will have the same speed of light. Meaning, if you have a rest reference frame, that'll have a certain speed of light, c, and if somebody is moving at a constant speed relative to that inertial reference frame, they will also see the speed of light as being c. It'll be the same 3.0 times 10 to the 8th meters per second for both observers in their own reference frame. What that means is the ether can't be detected. You can't do an experiment that observes a slower speed of light in any direction at all. Okay, so Poincaré basically proved that the Michelson-Morley experiment will never get you any results. Okay, he basically mathematically showed why, if the Lorentz effects are true, and they are, why the Michelson-Morley experiment was always destined to fail. And so this is where things stood after Poincaré. Ether was still considered to be the true absolute reference frame of the universe, and any other motion was apparent. Any other motion, you had your apparent time and distance, but the only true time and distance were in the ether's frame. But as Poincaré proved, okay, nobody could come up with an experiment to detect the motion through the ether. Impossible. So then there's this principle in science that says basically if you can't detect something, you should not assume it exists. Okay, so what was waiting for someone to come along and do was get rid of the ether, and that was what a guy named Albert Einstein did. So Einstein's real contribution to special relativity was he showed up and said, hey, if we can't detect the ether, we don't need it. It doesn't exist. And Einstein published a paper that basically showed that if you start from two simple assumptions, there's no need for an ether. Okay, all reference frames are relative. Under Einstein's special relativity, all reference frames are relatives. There's no true reference frame for the universe. Okay, there's no ether. There's no truly rest reference frame. So what are those two assumptions? Here they are. Number one is the same thing we've had since Galileo. The laws of physics are the same in all inertial reference frames. Okay, this is why you can be walking along the sidewalk, tossing a ball up and down, and it seems to be one-dimensional motion to you. It seems to be parabolic motion to somebody watching, but either one of you could do physics in your own reference frame, and you'll get the correct answers in your own reference frame. And then Einstein's second postulate for special relativity was that the speed of light in a vacuum has to be the same for all observers, regardless of how the source is moving. Okay, and this leads to some wacky stuff. Let me give you one example. Okay, so here's a situation where you have white holding a meter stick. His meter stick is 1 meter long, and red is moving past him at some fraction of the speed of light. Okay, I don't know what fraction this is, say it's 60% of the speed of light. So his meter stick is a little shorter. Okay? White observes red being shorter, or red's meter stick being shorter than his own meter stick. That's fine. Okay? But now Einstein said, and Galileo said before him, that any inertial reference frame should be just as good as any other. Why can't we use red's reference frame? So this is what we showed before, white's reference frame. But in red's reference frame, red can just say, hey, no, I'm motionless. I'm the one who's motionless. I've got the full 1 meter long meter stick. White is moving to the left. White ought to have the shorter meter stick, right? How can this possibly be that white thinks that red has a shorter meter stick and red thinks that white has a shorter meter stick? That doesn't make sense, right? You can't have, if A is greater than B and B is greater than A, that doesn't work. You can't have A greater than A because then it screws everything up, okay? So what's the answer here? What's the answer to this apparent paradox? So to get into that, what I need to do is show you something called a space-time diagram. This is something like the plots we've done before, except we reversed space and time. So now we've got time as the vertical axis and space as the horizontal axis. This is a common thing done in physics, okay? And I'll sort of show you why, okay? So any given point here on this space-time diagram is called an event. An event is a time and a location. It's a moment in time and a location, and it's where something either happens or doesn't happen, whatever. It's like a point in space, okay, except it's in this time x space, okay, or time position space. Okay, now these blue things are called world lines. World lines connect all the points or all the events that an object passes through in its history, okay? So here, for example, this first one, I'm moving the mouse cursor along, okay, is the world line of an object that's at rest, okay? All of these events on the blue line are events with different times but the same position, okay? So this is an object that's at rest, okay? This here, this slanty one, is an object that is moving at a constant velocity in the positive x direction. So you start off at time 0, or whatever the time is down here, and as time goes up, you move in the positive x direction. So this is an object moving in the positive x direction. Very simple. Now this one on the right is the trickiest one, but it's still not very hard. This is an object that starts off moving in the negative x direction, and then slows down and comes to a stop, and then after a while is moving in the positive x direction. This is an object with an acceleration in the positive x direction. So negative x direction velocity, slows down, stops, now moving in the positive x direction. Now, the thing about space-time diagrams is you can sort of animate them in your head by imagining a horizontal line, okay? Start the horizontal line down here, and then imagine the horizontal line sweeping upwards. So I'm trying to move the mouse cursor and show a horizontal line sweeping slowly upwards. And the places where these world lines intersect the horizontal line, those represent the positions of all these objects at a given moment in time. So at the beginning, you know, they're like, oops, sorry. At the beginning, they're like this, and then as time goes on, the middle one moves to the right one moves to the left, okay? Just sort of a way you can visualize these things. And one of those horizontal lines basically defines what's happening at one instant in time in the universe. It defines the state of the universe at one moment in time at all different positions, okay? So what we want to go to now is a variation on this discovered by Hermann Minkowski, okay? If you've heard the story about Einstein being bad at math and his math teacher saying he would never amount to anything, you may have heard that story. The part about him being bad at math is actually not true. He was extremely good at math. But the teacher who said he would never amount to anything was Hermann Minkowski. And Minkowski said that because Einstein never seemed to be paying attention in class. He was always doing his own math stuff. And he was asking all these really bizarre questions. But when Minkowski read Einstein's first paper on special relativity, he came up with this very interesting and useful geometric way to understand special relativity, okay? So Minkowski basically said, look, if you take the time axis, multiply it by c, what you've done now, c is the speed of light, okay? You take a speed in meters per second, say, multiply by time in seconds, and now you're left with a position in meters. So it gives the time axis units of length or position, like meters. And since you already have units of meters on the x-axis, you now have the same units on both axes, and then this just becomes like geometry. So this is called geometrizing the space-time diagram. Okay, so here now is the world line. This is nothing new. This is the world line of an object that's right here. Okay, it's moving in the positive x direction at a speed of v, so its world line moving at a constant speed is just like this. No big deal. Now let's say we have some event E, and there's a big flash of light at that event. Okay, it could be a firework going off. It could be just someone flashing a strobe light really quickly or whatever. Okay, light is emitted from that event. How does the light travel on the space-time diagram? Well, light travels at the speed of c, and it's not hard if you think about it a little. It's not hard to see that on a diagram with c times t being the time axis, the slope of the world line for light will be either 1 or -1. Okay? In a time of t, it'll move c times t distance, right? So the distance it moves on the x direction will be the same as the distance it moves in the time direction. Okay? So these green dotted lines are the light coming from event E. Okay, it shines in the positive x direction, the negative x direction. It would also emit light in the y and z directions, but we're only showing x here. Okay, and so the light spreads out. At this moment in time, the light has barely moved at all. Later on, like here, the light has moved, this far to here and here. Later on, it's moved further apart. Okay, etc. So here now is when this guy on the blue line actually sees the light. Okay, when it's right here, he doesn't know that this has happened. He hasn't seen the light from it. The light hasn't reached it. This is the light reaching him. So when you hear about, say, a supernova happening, we see a supernova in the sky, and somebody tells you, well, that supernova didn't just happen. It happened thousands or even millions of years ago. Okay, that's because of the time it takes the light to get to Earth. Okay, so it'd be a similar picture if, say, this dot here was Earth. Okay, we probably aren't moving this fast relative to any supernova or anything, but the same principle holds. Okay, where we have to wait for this green dotted line to reach us before we can actually see what happened back in the past. All right, so where am I going with this? I just want to recap. This is the paradox we're looking at, where white sees red moving to the right, red is shorter than white, red sees white moving to the left, white is shorter than red. What the hey? How can this be possible? So let's see. The next thing is right. Okay, so here's this plot. Okay, this is, let's just focus on the left side for a minute. Okay, this is a space-time diagram. This is a Minkowski diagram in Black's reference frame. And now what I want to do is, oh boy, let's see if I can. And sorry, give me a second to find. No. Well, let's try that. There we go. Okay, I needed to get my lines. Okay, so this is Black's reference frame. In Black's reference frame, Black is at rest. Black stays on the time axis. Okay, right? Doesn't move. Doesn't change x. Okay, and time passes like this. Okay, Black's got his or white, black. You know what I mean? Same deal. Okay. So I'm going to draw this line here, which is this is the world line for the left end of White's meter stick, and here's the world line for the right end of White's meter stick. So basically everything between these two lines is the space-time swept out by White's meter stick as it goes forward in time. Now I'm going to do the same thing for red. Let me get a red line there, okay? And here now is the world line for the left end of Red's meter stick. And here's the world line for the right end of Red's meter stick. Okay? So everything in this red parallelogram is what's swept out by Red's meter stick as time goes forward. Now let me draw, we'll do blue. Okay? Let me show you, here is where the left end of Red's meter stick passes the left end of White's meter stick, right? And over here is where the left end of Red's meter stick passes the right end, excuse me. This is where the right end's passed. Okay, so I'm going to go L and R like that, okay, to show you this is where the left end passes first. Whoops. Let's see if I can undo that. The left end passes first down here. The right end passes second up here. And so what white can say is, well, since red's left end passes first, that means for all this time in here, okay, red's meter stick is entirely inside of my meter stick. That means red's meter stick must be shorter. Okay, so white basically submits this as proof that white wins the argument. Okay, so let's look at how it works now. On the right-hand side, we'll look in red's reference frame. Okay, we have exactly the same situation, except that it's reversed. Okay, white is traveling in the negative x direction in red's reference frame, whereas red is traveling in the positive x direction of white's reference frame, but it's the same deal. It's the same situation. Okay, here's the world line for red's left. Oh, I'm going to just do it in red so I can keep the colors, nice and consistent. This is hard to understand under the best of circumstances, and I want to make it worse by doing wacky colors on you. Okay, so there's the left end of red's meter stick, and here's the right end of red's meter stick. Okay, and let's go now to black and do the left end of white's meter stick. Good enough. And the right end of white's meter stick to there. Okay. And now, what do we have? So, blue and drawing. And so now we can say, well, right here is where the right ends pass, and right here is where the left ends pass. Okay? And so red says, no, look, see this? Okay? The right ends pass first, then the left ends pass. Right ends, then left ends. So clearly, my meter stick is longer than white's. Okay? So they can both produce diagrams in their own rest reference frame. They appear to be longer than the other one. They can both say that. Okay? So what's going on here? Well, what's going on is that they disagree. I'll give you the answer and explain it then. They disagree about the order in which these events occur. Okay? White says that L happens first, then R. Okay? L being the left ends passing, R being the right ends passing. Red says that R happens first, and then L. What? Okay? So here's how we can make some sense of that. Let's say when white and red pass each other, there's a flash of light. Okay, they both emit, whoops, I won't do that. They both emit a burst of light there. Okay, the light travels at a slope of positive or negative 1. Okay, so there's the light going in the positive x direction. Here's the light going in the negative x direction. Okay, like that. And I'll draw it over on this side as well to be consistent. Okay, so there we go. Now, let's look over on the left-hand side. Look at white's reference frame, so the black c times t naught axis and the black x naught axis, okay? And notice that the path of the beam of light bisects these angles here, okay? So I can draw, let's see, I'll do this in black, but I'll say, look, in black's reference frame, this angle and this angle are the same, right? And also over here, this angle and this angle is the same. What are those angles over here? Actually, let me just go with the right hand set for now. Okay, I don't want to confuse things by drawing two different angles. They need to be the same. Okay, so let's look now over here and say, what is this angle here on the right hand side? Well, it's like this, right? So there needs to be an angle that's basically the same as this on this side between the x naught axis on this picture and the light. So we resolve that by basically saying what happens is over here in red's reference frame, white's time axis is slanted. White's space axis will also be slanted. Okay, now let me see if I can get this right. I need to have 9 for 15. So it's going to be about like that. That line there, let me draw this, is the x naught axis. And now you can see this angle and this angle within the limits of my drawing. Actually, I did pretty well, are the same. Okay? over here, now let's do the same thing for red. Let's draw red's space axis, okay? Red space axis, I'm not going to go through the logic here. Red space axis, though, will look like this, okay? And now you can see this angle here and this angle here. So this one here between the black and the, between the green and the red, and between the green and the red here are the same, just like this angle between green and red and this angle between green and red are the same, okay? So what does the space axis signify? The space axis signifies all the things that are happening at one moment in the universe, okay? So if you look over here, let's look at the black dotted x naught axis, okay? At this moment in time, this is a snapshot of the universe at time t equals 0 in in White's reference frame, okay? And it says, well, here's the left end of White's meter stick, here's the left end of Red's meter stick, here's the right end of red, and here's the right end of white, and so clearly white is bigger than red. But if you want to look at the same moment in time from red's point of view, okay, what does red's snapshot of the universe look like? Okay, here you've got to use this red x1 axis, this one going here, and you say, okay, so here is red's left end and then white's left end, and then down here is white's right end and red's right end. And so you can see now in this picture, if you look along this axis here, you can see red is clearly bigger, right? Here's red, and they're outside of black and black, okay? Those points I just circled on this plot are here, 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 here. So this is how you resolve this paradox. Which one has the longer meter stick? Well, it depends on whose reference frame you're asking the question in. And this thing like the order of events here, okay, do the left ends pass? Does event L happen before event R, or does event R happen before event L? That also depends on whose reference frame you're looking at. And that makes things kind of tricky. It can kind of screw a little with your philosophy of the universe if events don't always happen in the same order. If it can depend, if the ordering of events can depend on your motion. Whoops. Sorry, my screen went off for a second. No, I'm okay. You can't screw with it too much, okay? And I'll show you that in the next video. So anyway, that's the resolution of that paradox, and hopefully this tells you a little more about how special relativity actually works and why it does not create these unresolvable paradoxes. Okay. No, wrong thing. Whoops. Sorry, I just opened the App Store for no good reason.